So our next speaker is Chris Chamberland from the AWS Amazon Center for Quantum Computing. So he's my recent colleague and he's going to be talking about a topic very dear to my heart, magic states. So take it away, Chris.
All right, thanks everyone, and thanks Marcus for the great talk. So today I'll be talking about work that was done in collaboration with Kyungju No at the AWS Center for Quantum Computing. And so the goal of this work was we'd like to build a universal fault-tolerant quantum computer. And we'd like to do so in a way that really takes hardware considerations into account. And when I say that, what I'll be having in mind is mainly a superconducting qubit architecture. So we're going to require that the qubits are laid out on a two-dimensional plane and that they interact via nearest neighbor interactions. So those are going to be the hardware constraints that I have in mind throughout the talk. And then the question we'd like to ask is, can we devise a scheme of universal fault-tolerant quantum computing in the setting that has a really low overhead, at least relative to what's been done before. There are many techniques for doing universal quantum computation, but I believe that it's still the case that magic states and magic state distillation is one of the leading candidates. And as you heard in Marcus's previous talk, there's been a lot of recent developments in the area of fault tolerance, and in particular by using flags. And these are tools that are extremely useful to prepare states of interest. And in this case, it's magic states. And so in this talk, what I'll show is how we can fault tolerantly prepare magic states instead of doing magic state distillation. And I'll kind of be very specific about what the differences are between magic state distillation and fault tolerant preparation of magic states. And the idea will be that due to the fault tolerance of our circuits, we'll be able to prepare magic states with extremely low overhead compared to magic state distillations in some regimes. Okay, so I'd first like to just give a brief summary of the different kind of schemes that we have for universal quantum computation. And this list here is certainly not exhaustive, and there's a lot of other methods that aren't going to be mentioned here, but I guess these are the most common ones. So like I mentioned before, there's this idea of magic state distillation, which I'll get into in the next slide. And then there's this, these ideas that I've been working on, which is to fault tolerantly prepare these magic states. And that'll be the main focus of this talk today. But there are other methods as well, such as code switching. So this is where you have, say, two codes where when you take the transversal gates in both codes, they form a universal gate set. So when you want to do a particular gate, which is transversal in, say, code A, you use code A. And then if you want to do the gate that's non-transversal, you would fault-tolerantly switch to the other code where that gate is transversal, do the gate in that code, and then switch back in a fault-tolerant way when you want to do the other gates. There's other methods such as transversal gates and error correction. So the idea here is that the gate, the gate which is not transversal, you would implement that gate in a transversal way and then do some rounds of error correction. And by doing that, you would gain information on the essentially corrections you have to apply to restore the code space after you've done the transversal gate set. And so that gate which is non-transversal, you do transversely, and all the other gates are transversal, so you get a universal gate set in this way. And then there's this idea of peaceable fault tolerance. So this is where you have a gate which isn't transversal, but you write down the circuit, and then you do intermediate rounds of error correction at strategic locations within that circuit. And in that way, you can control how errors propagate, even though not all the gates are transversal. And if you do it in the right way, you can implement the whole gate in a fault-tolerant way. And then there's also the idea of universal concatenated quantum codes. So this is kind of similar to code switching. So you have two codes where the full universal gate set is transversal when you have both codes. And then you concatenate both of these codes, and then you obtain circuits for doing these gates in a fault-tolerant way, even though they're not transversal in one of the two codes. At the cost of having a reduced code distance. So that's how you would circumvent the Easton-Knell theorem. Okay, so I'm going to start by just talking about what magic state distillation is. And I'm going to refer to magic state distillation as a top-down approach, and I think that'll become clear when, as we move along in the talk. So as I mentioned before, magic state distillation is one of the leading candidates for doing universal computation. And the reasons is that, especially for the kind of architectures that we have in mind, so qubits that are laid out on a two-dimensional plane and that interact via nearest neighbor interactions, the techniques for distilling magic states and then using them to simulate all gates in a universal gate set are very well known. And there's been a lot of developments in this area over the last 10, 15 years, and the costs of distilling these magic states have been brought down quite significantly. And the techniques are kind of pretty well suited for the connectivity constraints and the qubit layouts that we have in supernetting qubit architectures. And so the idea of magic state distillation is to take, say, M noisy magic states, which we want to use to simulate all our, our non-transversal gates and our universal gate set. And then we're going to do some operations and produce N output magic states where N is less than M that are higher fidelity than the ones that were injected. The reason these are called magic states is that they can be distilled using only stabilizer operations, and at the same time, they can be used to simulate gates in universal gate set using only stabilizer operations. Okay, and then the idea of how we're going to purify these magic states is that we're going to use some error correcting code that can detect errors on these noisy magic states. But the key feature here is that the stabilizer circuits, or the circuits that we're going to use to detect the errors in the magic states are not fault tolerant to failures in our stabilizer operations. So what is typically assumed is that these stabilizer operations are going to be encoded in a very large code, or at least where the distance is chosen such that the failure rate of all our stabilizer operations are comparable to the fidelity of the magic states that we want to prepare. And then this code doesn't have to be the same code that we're going to use to detect errors in these noisy input magic states. So those are two separate things. And then we'll use these encoded gates with a very efficient distillation protocol to purify the magic states with the lowest cost possible. But so as you can see, kind of from what I've been saying, one of the reasons that magic state distillation is very costly is that you do need to use these encoded gates in a high distance code. There's certainly room for improvement here, because if your circuits are fault tolerant to Clifford operations, then you wouldn't necessarily need to encode your Clifford operations or your stabilizer operations in a large error correcting code. And so that's something that we're going to take advantage of in the techniques that we present in this talk. So I'd like to give an example of a magic state distillation protocol, but first I'd like to take this opportunity to introduce some notation, because the notation that I'll be introducing here is something that I'm going to use throughout this talk. So the magic state of interest that we're going to want to prepare is what's known as the H state, which is a +1 eigenstate of the Hadamard operator. And the state is given here. It's related to the 0 state by a T gate, where this is a non-Clifford gate. And the T gate is represented by this matrix. And so the reason why an H state is a magic state is because it's related by Clifford operators, so Hadamard and phase, to the state A power 4. And this state A power 4 could be used to simulate a T gate. So with repeated, so if we have the state A power 4 in stabilizer operations, we can use those things to implement a T gate, which is a non-Clifford gate. Okay, and so one of the nice things about the H state is that one can detect errors by measuring the Hadamard operator, right? So let's say our state is affected by a Y error, so it maps H to -H. We can use the circuit that you see here, where we prepare plus, do control Hadamard and measure in the X basis. And this would detect a Y error present on the H state. And furthermore, if we have X or Z errors, the measurement outcome here would be probabilistic, but if we measure +1, we'll end up projecting the H state to a state that has no X or Z errors. And if we measure -1, then we would detect that there was an X or Z error on that state. Now, to see that you can do everything here by using only stabilizer operations, this control Hadamard gate used for measuring Hadamard can be decomposed into a control Z and then a product of two T gates. And the T gates themselves can be decomposed into a circuit where you have only stabilizer operations and an input magic state, right? So if you replace T by the circuit that you see on the bottom right of the slide, then you can see that this whole, the entire control Hadamard gate can be done by using only stabilizer operations and copies of, two copies of H states, right? So now what we'd like to do is to use an error correcting code to be able to prepare these magic states with very low fidelity. And so I'll very briefly present one way of doing this. So, and I'll come back to this slide in a lot more detail in the remaining parts of the talk. But one idea is that you could use the Steane code, which is the smallest version of the color code. And what's nice about color codes in these cases are that the logical Hadamard operator is a transversal Hadamard. So it's just H tensor N for an N qubit color code. So for the Steane code, if you wanted to measure the Hadamard operator, you can just do this sequence of control Hadamard gates. And you'd get this protection from the color code. And one of the things that Ben Reichart realized a while ago was that this protocol is equivalent to the well-known 15 qubit protocol for magic state distillation up to Clifford gates. But the point here is that up to Clifford's for practical purposes is extremely important because it could have very significant implications on the space-time costs between two magic state distillation schemes that are equivalent up to Clifford's. So I'm going to come back to this very shortly and explain this in more detail. But now I'd like to present kind of the main ideas of what's being introduced in this work. And so magic state distillation is a top-down approach, right? Because we don't care about the fault tolerance of our stabilizer circuits. We just say, look, it doesn't matter if the circuit's not fault tolerant, as long as it can detect errors from these noisy magic states, we're going to encode our stabilizer operations in a large error correcting code. And so we won't have to worry about failures in those stabilizer operations. So here, the idea is to prepare a magic state in a very direct way, using fault-tolerant circuits from the very beginning. And so this is what we'll refer to as a bottom-up approach for magic state preparation. And as I just said, the idea is that, okay, we have these noisy magic states that we want to distill. But what we're going to do is we're going to design our circuits to purify these magic states that are fault-tolerant to stabilizer operations, to failures in our stabilizer operations. And so we could use physical gates instead of encoded gates to obtain high quality magic states. And so the cost of doing each gate is going to be significantly lower than if we were to use magic state distillation. And so there was one paper where I introduced these ideas, but we didn't really think about connectivity constraints and just having qubits on a two-dimensional layout. And when you do think about these things, there are new ideas that are important. So as you heard in Marcus's talk, flat qubits are going to play a pretty important role here to make our circuits fault tolerant. But the point I want to make here is that flat qubits are not going to be enough. We're going to need something new, which is what we call redundant ancilla encoding. And this idea of redundant ancilla encoding really comes into play when you take these hardware constraints into account. And so I'll describe that in quite detail in the coming slides. So before explaining how we're going to prepare these magic states, and for our well, in this talk, we're going to prepare the H states that I introduced a few slides ago. I'd just like to briefly remind you about some of the features of the color codes. And Marcus talked a lot about this, so I'll be very brief in this slide. But the color codes that we're going to be focusing on here are triangular color codes because they have the lowest weight checks. And they're obtained by taking tilings of hexagons and then cutting the tiling of hexagons by a triangle, an equilateral triangle. And the size of the boundary of the triangle is going to determine the distance of the color code that you end up having, right? And here the data qubits are going to be on the vertices of these hexagons. So these would be the yellow dots that you see in this picture. And the stabilizers are going to be the colored plaquettes. So each plaquette consists of both X and Z type stabilizers. And so if you think about memory, right, because a lot of people ask, you know, the surface code has much better thresholds than color code. So why do we even care about color codes? And that's certainly true, right? And kind of two of the reasons why surface codes have better thresholds is that they have lower weight checks, right? Because you see here we have to measure weight 6 stabilizers for color codes, whereas for the surface code, the highest weight stabilizers are 4. And in addition, you know, you have both X and Z stabilizers at each plaquette, so you have to measure them sequentially. You can't measure them in the same scheduling as you could for the surface code. So the circuit depths are going to be larger. And that's something that really matters, especially when idle qubit errors are high, as is the case in superconducting qubit architectures. For ion traps, you know, idle qubit errors are very small compared to 2-qubit gates, but that's not necessarily the case for superconducting qubit architectures. And the other reason is that decoding color codes is harder than decoding surface codes. However, for doing gates, color codes are extremely useful, and you'll see why in the remaining parts of the talk. But the feature that we're going to take advantage of here is that the Clifford operations are transversal for the color code. So phase and Hadamard, in particular, Hadamard is just a tensor product of Hadamard on every qubit. And in addition to that, you know, color codes have the nice feature that the qubits can be laid out on a 2-dimensional plane and interact via nearest-neighbor interactions. And so that's another thing that we're going to take advantage of. So in a previous slide, I showed you the circuit for measuring Hadamard, right? And of course, when we care about fault tolerance, we have to have a little bit more than that. Because, for instance, if I have, excuse me, an X error, oops, on the control qubit of a control Hadamard, it can propagate to a high weight data qubit error. And so errors like this need to be detected. And that's where these flag qubits come in. So in this particular case, the flag qubit would be the qubit that's prepared in the 0 state. And this is a circuit for a distance 7 color code, so the Steane code that I showed you before. And so if there's a single fault, a single failure on any of these control Hadamards that propagates to a minimum weight data qubit error, which is greater than 1, then that will always be detected by this flag qubit. So instead of measuring it in +1, you'd measure it in -1. So we'll say that a flag qubit flagged when its measurement outcome is non-trivial. And so that's great. The problem is, though, that a circuit like this isn't really suitable for qubits that are laid out on a 2-dimensional architecture and that interact via nearest neighbor interactions. So if we want to do something like this, we're going to have new ideas. And furthermore, as we go to larger color code distances, we're going to need more flag qubits to improve the fault tolerance properties up to the full code distance. And I'll explain exactly what I mean by that in the previous slides. So before going into the details of how our scheme works, and when I say our scheme here, the goal again is to prepare an encoded H state encoded in the color code and to prepare it in a fault tolerant way. So, so before explaining the details of how that works, I'd like to give a big picture idea of what the scheme is going to consist of. So there's going to be essentially 3 steps. The first is going to be to take a physical H state and then grow it into a state which is encoded in the color code. And we're going to want to do this using the hardware constraints that I've been talking about. And then the second step is to measure the Hadamard operator. So for instance, implement some circuit like this to detect logical failures that can happen on these H states during the growing process. And then of course, the third step is to do a round of error detection. So we're going to measure the stabilizers, the X and the Z stabilizers of the color code to detect additional errors. And this process of measuring the Hadamard and then doing a round of error detection is going to be repeated d-1 over 2 times. And just to be very, very clear, the box here that you see, which is ECD, this is 1 round of X and Z stabilizers. So we don't repeat the stabilizer measurements here. And similarly, HMD represents the circuit for measuring the logical Hadamard operator of the color code once. And so the sequence of Hadamard measurement, error detection, that is repeated d-1 over 2 times. And here d is the distance of the color code that we're using. And I just want to point out, it's very important for this whole process to be fault tolerant, to do things in this order. So if we were to do, say, all the error correction at the very end, and then do the Hadamard measurements first, that would not be fault tolerant. And if you want to know more details as to why that's the case, you can read our paper, and in appendix we give a proof of that. Okay, so now let's dive into the details in each of these steps. So I'll first describe how do we do this growing process. So so here we want to take a physical H state and encode it into a logical H state of the color code. And this is, you know, the techniques for doing this are fairly well known. So the idea is to start with a stabilizer state. So so you have, say, in this case, the whole color code. This is an example of distance 5 color code, has 19 qubits, and 18 of these qubits are encoded in the stabilizer state. And so a stabilizer state is a state that doesn't encode any logical qubits, and each plaquette here is a stabilizer for that stabilizer state. And you'll see that you have these weight 2 stabilizers at the boundaries of the triangle. And just to point out, the boundary here isn't really important. I just chose one of the sides for illustrative purposes. And now the way that you would prepare the state is that you would measure these, the operators in the white plaquettes at the boundary. And so these operators don't commute, right, with these weight 2 operators of the weight 2 stabilizers of the stabilizer state. And so those measurement outcomes are going to be random. And now the question is, based on -1 outcomes, we have to figure out what corrections we need to apply when we do measure -1 to project back to the code space. And there are many ways for doing this, but a very straightforward way is to take this one-dimensional graph here that you see on the right, where the vertices just correspond to the measurement outcomes of these white plaquettes, and to do minimum weight perfect matching on this graph. And if an edge is selected, you do ZZ corrections on the qubits that correspond to this edge. So for example, the edge E2 here corresponds to the 2 qubits that you have here. And so you do those corrections if the measurement outcome, well, let's say that these 2 vertices were highlighted, and you would choose the edge E2. Now, of course, there can be measurement errors. There could be gate failures. So what we have to do in this case is we have to repeat, once we've measured the white plaquettes, we have to repeat the measurements of all the stabilizers of the color code, and to repeat those measurements order d times, and then to implement minimum weight perfect matching over the whole syndrome history. And then we'd be able to figure out if there were measurement errors if we do this enough times, assuming the total number of failures isn't too high. And then do the appropriate corrections to project to the code space. So this is all great, but of course, this whole thing isn't fault tolerant. And what I mean by this whole process not being fault tolerant is that you know, our goal here is to prepare an H state encoded in the color code that has a failure probability p to the d+1/2. And here P, I'm assuming a depolarizing noise model for simplicity, where every component of the circuit, say gates, measurements, idle qubits, and state preparations, fail with probability P. And D here is the final distance of the color code. But indeed, a single failure, say on a physical H state, could cause a logical error during this growing process. So that's where these other steps come in to make the whole thing fault tolerant. Okay, so now I'll describe, the steps 2 and 3 in the process for preparing this H state. But instead of starting with Hadamard measurements, I'll start with doing error detection, and I'll explain why. So now the key is, okay, we have this nice growing step, and now we want to have a way to measure the stabilizers of the color code in a fault tolerant way. And in this paper by myself, Alice Kubica, Ted Yoder, and Guanyu Zhu, what we showed is that for the color code, you only need 1 flag circuits to measure all the weight 6 stabilizers of the color code. And what I mean by a 1 flag circuit is the following. In general, a V flag circuit is a circuit that has the property where if there are V failures during the stabilizer measurement or the measurement of the operator of interest, and those V failures lead to a minimum weight data qubit error of weight greater than V, then at least one of the flag qubits will flag, okay? And V here is taken to be less than or equal to D minus 1 over 2. So in the case of the color code, right, we have these weight 6 stabilizer measurements that we need to perform. And so we need to have a one flag circuit, meaning that if there's a single fault, say that leads to a data qubit error of weight 2 or 3, we want at least one of the flag qubits to flag. But an interesting thing is that we don't need a 2 flag circuit. And the proof of this is given in the reference that you see at the bottom. So we've constructed one flag circuits for measuring the stabilizers of the color code, which is obtained using the layout that you see here. Okay, and so the gray vertices here are the ancilla qubits that are used to measure to measure the parity of the stabilizers, and the white vertices here are the flag qubits, and the C naughts are arranged in a way such that this circuit is one flag. Now you're gonna notice something quite strange, right? We need these flag qubits to ensure fault tolerance, but we don't need these extra ancilla qubits, right? We really only need one ancilla qubit to measure the parity of the stabilizers. So the extra ancillas don't give us any useful information. And indeed, if all we cared about was to do error correction, then this would be, major overkill, right? We'd be using resources that we don't really need. However, when we measure the Hadamard operator, what's going to happen is that these ancilla qubits, their roles are going to be reversed. So the ancilla qubits are going to become flag qubits, and the flag qubits that you see here, the white vertices, are going to become the ancillas needed to measure the global operator, which in our case is the Hadamard, of the logical Hadamard operator of the color code. And the reason that this all happens is because we want to use the same architecture and the same qubit layout to measure both the stabilizers of the color code and the logical Hadamard operator, right? And so this is what I mean by redundant ancilla encoding, because we're using a redundant amount of ancillas to measure the stabilizers, but those ancillas are going to become flag qubits when you measure the global Hadamard operator, and those flag qubits are going to be crucial to ensure that measurement process is fault tolerant. Okay, so that's what I'm going to explain in the next slide. So, the sequence for measuring Hadamard is a little complicated, so I'd like to start with the simplest case, which is the distance 3 color code, just to give you a flavor of what's going on. So for the figure on the right, we have the layout that we introduced before for measuring the weight 4 stabilizers of the smallest color code, the Steane code. And as I mentioned in the previous slide, when we measure the logical Hadamard operator, there's this role reversal between the ancilla and the flags. So as you can see here, for example, this gray vertex becomes a white vertex, so it's a flag when we measure the when we do the control Hadamard gates to measure Hadamard. And similarly, the white vertex here, which was a flag for the stabilizer measurements, becomes an ancilla when measuring Hadamard, okay? And what we're doing here is we're preparing a GHG state to measure the Hadamard, and we're going to use these flag qubits to make that whole measurement process with the GHG state fault tolerant. So how does this work? Right, I'm just giving you a pictorial representation of what's happening. So we do the C0 gates between all the gray vertices, right? And what this does is it prepares the GHG state. Once we have the GHG state, we can do our control Hadamard gates to measure the logical Hadamard operator of the color code. But then we have these additional flag qubits, the white vertices here, and we do C0 gates between the gray vertices and the white vertices. And we do them in such a way that, in this case, because it's a distance 3 color code, this whole measurement process is one flagged, right? So we're gonna, whenever there's a failure and it propagates to a bad error on the data qubits, these flag qubits are gonna detect that process and flag. And then of course, at the last step, we have to measure these ancillas, right? So to, maybe make things a little clearer, writing down the circuit on the right here, this is exactly what I was describing. And I just want to point out that when you do this measurement, the gates aren't necessarily done in this sequence. So you don't necessarily first prepare the GHG, then do control Hadamard, then do the C0s for the flag qubits. This is all done, simultaneously, or you're kind of mixing up things in the circuit here. And, you know, the point that I want to make here is that the C naughts are cleverly chosen such that these circuits are one flag, and that's finding the right sequence of C naught gates is a highly non-trivial problem, and that's not something that I'm going to have time to describe in this paper, or sorry, in this talk, but you can read the paper for more details. So now I just want to show the slight generalization of this when we have higher distance color codes and we need to measure these weight 6 operators. So what happens is we use this ring-like structure that I showed you before for doing the stabilizer operations or the stabilizer measurements of the color code. And now we can use the same layout to to measure the Hadamard operator, right, for the higher distance color codes, and use these flag qubits to detect bad errors that happen. Okay, and this could be this ring-like structure with the kind of gate sequence that you're seeing here. This works for distances up to distance 7. And the unfortunate thing is that if we want to have a circuit which is fault tolerant for color code distances which are greater than 7, then we need to pack more qubits within these weight 6 checks and the weight 4 checks as well. So that's potentially a problem, right? So these circuits are 3 flag. And so what I mean by that is that if there are, say, 3 failures which results in a data qubit error of weight greater than 3, then at least one of the flag qubits in this whole sequence, or in this whole circuit that you see here, is going to be measured non-trivially. And whenever you have a non-trivial measurement outcome, whether it's for the flag qubits or for the measurement of Hadamard or stabilizers, excuse me, you would reject the whole protocol that I showed you before and start the whole process over again. So now, before showing overhead results for the performance of our schemes, I'd like to talk a little bit about scalability, because you might be asking, well, if this works for color codes between distances 3, 5, and 7, how do you scale this? So there's a few things to say here. The first is that because this whole process is an error detection scheme, even if we did have a circuit for higher distance color codes, the acceptance probability drops exponentially with the distance of the color code. So for practical purposes, we don't want to use distances which are too large. And the other thing is that we could use, if say a distance 7 color code isn't enough, right, to get what we need, one thing that we could do is to use encoded gates, right, similar to what's done in magic state distillation. But the great thing here is that because the circuit is fault tolerant, the distances of these encoded gates will not necessarily have to be, well, they won't have to be as large as what would be required. So typically in magic state distillation, you choose the distance based on the fidelity of the magic states that you want. And say you want a magic state with a particular failure rate, you would choose a distance such that the failure rate of your Clifford gates are less than or equal to the failure rate of the magic states that you want. But here, that's not going to be necessary because these circuits are fault tolerant. So, and as I'll show you in the last slide, we can get very, very low failure rates in magic states using very small distances in this whole in this whole protocol. So let me start by showing you results. And so here, the goal is to say, look, let's say that our failure rates are on the order of 10 minus 4. For most of the practical purposes, for most of the algorithms of interest, we want failure rates or magic states that fail with probability at least 10 minus 8. And if we get magic states with failure rates of 10 minus 10, that would be even better, right, for a lot of the interesting algorithms. Okay, so if you look at the table on the top right of the screen, you can see that using a distance 5 color code allows us to get magic states with failure rates on the order of 10 minus 8 using only 55 qubits. And similarly, if we want magic states with failure rates on the order of 10 minus 10, we can use a distance 7 color code and use only 118 qubits to do this, to prepare those magic states. And I want to compare these numbers to the best known magic state distillation schemes. And so the numbers that you see here for the table on the bottom of the screen, those were obtained from a paper by Daniel Litinsky, which had very highly optimized magic state distillation protocols, where he's optimizing over the distance and the layouts to use the fewest resources possible to prepare magic states with failure rates that are similar to the ones that I'm showing you at the top. And you can see here that for an error rate of close to 10 minus 8, you know, the number of qubits that are required is 810. And similarly, for 10 minus 10 failure rates, or 9 times 10 minus 10 in this case, you need, you know, over 1,000 qubits, whereas in our scheme, you would need around 118. So, you know, there's about an order of magnitude and more improvement using these fault-tolerant protocols. And for example, 55 qubits to get magic states of error rates of 10 minus 8, I think that's something that we could use in near-term quantum computers that are currently being built. And so I think that these kind of schemes offer, you know, a lot of potential for doing computation with near-term quantum devices. Now the caveat, right, is that the error rate regime that I'm looking at here is 10 minus 4, right? And I think practically speaking, we'd like to be a little bit closer to 10 minus 3. And furthermore, one can ask, well, how do we get even lower failure rates, right, than 10 minus 10? For instance, if you want to implement very large quantum algorithms, like factoring a 2,000-bit number using Shor's algorithm, then you'll need, you know, lower error rates for the magic states, something around the order of 10 minus 15. And this comes into the idea of using these encoded gates that I talked about before. So just to give a pictorial representation of what is happening. So you know, our scheme can be generalized, right, using additional steps if we want to use encoded gates. Okay, and the idea is to have the same kind of protocol. So we have a distance which I call DF color code, which is going to be 3, 5, and 7. And so this is the distance that we want to use for the color code to measure Hadamard. But the gates now are going to be encoded in either the color code, but we could also use gates encoded in the surface code, right? So the way that you do this is you would first start by preparing magic states of distance D1 using the schemes that I showed in the previous slides. And then you grow these magic states to a distance D2 magic state. And this process is fairly straightforward, and I'll show how it's done. I'll give an example of how it's done in the next slide, but it's pretty much the same idea of what I've shown before. And in addition, for the control Hadamard gates used for measuring Hadamard here, right, we can't do physical T gates, right? In the previous step, remember that the control Hadamard gate can be decomposed into a CZ gate and then 2 T gates. But this was all done at the physical level, right, because of the fault tolerance of our schemes or of our circuits. But here, right, we're going to be using encoding operations. So we're going to need to inject magic states to do those T gates, right? So what I'm showing here is that we're going to grow our magic states at distance D1 to a distance D2 magic state, and then use those to do the T gates that we want for the control Hadamard gates in the encoded version of the Hadamard measurement circuit. And then of course we do error correction, and all of the gates here are transversal because these are all stabilizer operations. Now, if you want to use surface codes gates, right, there's an additional step that you need to do, right, because the H bar D2 state, this is going to be a state encoded in a distance D2 color code. So you need to teleport it to a distance D2 surface code. But there are ways for doing this, and in the numerics that I'll show you in the previous, in the next slide, this is something that we did take into account. However, we did not take into account the routing costs for doing the encoded version of our scheme, and that's something that's pretty important. And if I had to estimate, you know, it might change our results by a factor of 2, but that's something that we'll be considering in future work, how to include routing costs when doing the encoded version of our scheme. And before showing you the numbers, you know, I said growing a distance D1 to a distance D2 state is pretty straightforward. So you can see from this picture here, I'm just showing how to grow a distance 3 color code encoded states to a distance 7. And it's pretty much the same idea, but now you have additional white plaquettes at the boundary between the top color code patch and the bottom stabilizer state. And you do the same thing as before, and the corrections to project back to the code space would be given by doing min-weight perfect matching on this one-dimensional state, on this one-dimensional graph, and then you repeat the stabilizer measurements of the whole distance D2 color code to deal with the measurement errors. So what error rates can we get by doing this? So let me just focus on the surface code results. So in this table that you see at the bottom, we wanted to get error rates that were at least 10 minus 15 and show that it was possible, and also do that in a regime where the physical error was 10 minus 3. And what we showed was that for physical errors of 10 minus 3, if you use a distance D2 surface code and a distance 7 version of our scheme, starting with a distance 1, so we first prepare the magic states in a fault-tolerant way using a distance 1 version of our scheme, and then grow it to a distance 11 color code, and then teleport it to a surface code. And then, so we're using distance 11 encoded gates in a distance 7 version of our scheme, okay? And this gives failure rates that are on the order of 10 minus 20. And the number of qubits that we need to do that is around 60,000. And if the failure rate is around 10 minus 4 instead of 10 minus 3, then we need around 10,000 qubits to get a magic state with a failure rate on the order of 10 minus 17. So that concludes my talk. Thank you very much.
Okay, thank you, Chris, for a great talk with some very impressive numbers. So we've got a question from Andrew Landau. So have we got him? Can we enable his audio and video? Andrew, would you like to ask your question?
Sure. Can you hear me?
Yes, we can.
Okay. Well, it's written in the Q&A box. I'll essentially read it to you if you haven't read it already. So for three-dimensional color codes, the T gate, which I define slightly differently from you, I define it as sort of the fourth root of the Z gate. The T gate is transversal for these codes, but the Hadamard gate isn't. But the plus state is the magic state for the Hadamard gate in that situation. And you can prepare a logical plus state by doing error correction, which is not transversal. So that's how you get around the Easton-Nil theorem. And you might be able to do that in a growing way too, where you prepare a physical plus state and inject it, but you might be able to do it more directly. And I was wondering if your scheme is essentially the analog of this process for 3D color codes, but kind of mapped to measuring a different observable in 2D color codes.
Yeah, I think so. I mean, we didn't think too much about 3D color codes just because we wanted to use these two-dimensional constraints, or just have that in the back of our mind. And so in the two-dimensional version of the color code, the Hadamard gate is transversal, which is what we use to prepare our magic states. But I think you're right.
Okay, thanks.
Okay, thank you. Does anyone else have a question that they want to ask now? Don't appear to be any questions here, but Chris, do you have access to the Slack channel?
I do, yes.
Okay, well in that case, I suggest that we move any further questions onto the Slack channel, where there tend to be questions quite often. And so we'll all thank Chris, and we'll move on to the next speaker.